Welcome back to the Gaussian lecture series. In lecture 1, we learn how to translate chemistry into computation. Today, we go deeper. We answer a fundamental question: what does Gaussian actually calculate? What does those energy curves really mean? I don't know how much experience you have with Gaussian or computational chemistry, but I want to make one thing very clear. The picture that shows energy curves and surfaces are not just random graphs or abstract drawings. They represent real chemistry. Even if you have not worked much with molecular structures, these ideas are very important. In computational chemistry, we usually begin with an experiment or a chemical question and translate into a calculation, or more commonly, a sequence of calculations. These calculations rely on approximations. There are many types of approximations in quantum chemistry. The one we discussed is absolutely fundamental to all computational chemistry method, the Born-Oppenheimer approximation. The Born-Oppenheimer approximation, as we know, a molecule consists of atomic nuclei, positively charged heavy, and electron, negatively charged very light. The crucial difference is not just charge, it is mass. Nuclei are thousands of times heavier than the electron. Because of this, nuclear motion is slow, electronic motion is very fast. Electrons recognize themselves much more quickly than nuclei move. So, nuclear and electronic motions can be separated due to their different time scales. In practical terms, this means we fix the nuclei in a space, we solve for electronic distribution corresponding to that nuclear arrangement, we compute the total electronic energy. So, the energy becomes potential V of R. This is the potential felt by the nuclei. The nuclei move on that surface. In Gaussian calculation, we must specify the position of the nuclei, the number of the electron by charge, multiplicity. The Gaussian computes the energy using the chosen method like Hartree-Fock, DFT, MP2, MP4, detail of which depend on the level of the theory selected. Gaussian is a quantum chemistry program. It solves the electronic Schrödinger equation. For every arrangement of atom in a space, Gaussian computes the electronic energy of that geometry. Once we accept that nuclei are fixed during the electronic calculation, we can vary their position and observe how energy changes. Imagine a simple molecule like H2. If you move the two hydrogen atoms far apart, they are very high in energy. Bring them closer, energy decreases. Bring them too close, energy increases again. If you plot bond distance and energy, you get an energy curves. When we vary only one coordinate, such as bond length, we obtain our potential energy curves. This curve tells you where the molecule is stable, a minimum bond length, and dissociation energy. That's not abstract. This is the real measurable chemistry. For molecule with more than two atoms, there are many ways to move the atoms. The system has many degrees of freedom. The energy depends on multiple coordinates simultaneously. When energy depends on more than one coordinate, we obtain a potential energy surface. You can imagine this is a multi-dimensional landscapes. Valleys where we get a stable structure, a minima, mountain passes transition states, and a peaks high energy unstable regions. Most of computational chemistry involves exploring these multi-dimensional potential energy curves, surfaces, and interpreting chemically meaningful points on it. It is called potential because we are not explicitly allowing the nuclei to move with kinetic energy during the electronic calculation. That energy behaves like a potential energy functions of nuclear motion. So, instead, we calculate the potential energy as a function of nuclear position. Nuclear motion like vibrations, reaction dynamics occur on this surface. What does Gaussian actually calculate? In Gaussian, we specify the nuclear coordinates, compute energies, allow the program to adjust coordinates automatically, search for stationary points. A stationary point satisfies two conditions. The first, derivative energy gradient should be equals to 0. The energy does not change to the first order with small displacement. There are two important types. Minimum. First, minimum. First derivative should be equals to 0. Second derivative, curvature is greater than 0 in all directions. Energy increases if atoms are displaced in any direction. This represents a stable molecular structure. If you slightly perturb the nuclei, the system tends to return to the minima, saddle point, and also called a transition state. It should also follow the first derivative energy gradient equals to 0, but one direction has a negative curvature. This represents a reaction barrier. You will typically study this later in more advanced calculations. In Gaussian, nuclear positions can be specified in Cartesian coordinates like x, y, z, internal coordinates like bond length, bond angle, dihedral, torsional angles. These internal coordinates provide direct chemical insight. For example, in excited state chemistry, such as photoexcitations, bond length often change, bonding character may differ from the ground state, measuring bond length shift provides chemical understanding. Simply starting at Cartesian coordinate rarely give an intuitive chemical insight. Everything we discussed today, from the Born Oppenheimer approximation to potential energy curves and potential energy surfaces and geometry optimization in Gaussian, all these form the backbone of modern computational chemistry. When we fix a nuclei and calculate electronic energy, we are not just running software, we are translating chemistry into physics and mathematics. Every minimum corresponds to a real structure. Every saddle point corresponds to a real reaction barrier. Every curve and surface encodes chemical meaning. In the upcoming lecture, we will go deeper into how Gaussian actually searches for minima and transition state. If this lecture helps you understand computational chemistry more clearly, make sure to like the video and subscribe to the channel.